short summary video where we're going to talk about Diploma Program Physics 4.3, and that's wave characteristics. First we have to know what a wavefront and a ray are. Well, a wavefront shows parts of the wave that are in phase, and normally we show crests, or a wavefront shows the crest of a wave, that is the place where we have maximum displacement, and a ray shows the wave direction. And there are basically two types of wavefronts and rays. So let's say we have a planar source of waves. This could be, for example, the sun's rays as seen from far off, or deep sea waves, for example. So if I look from the top down on the waves as they come into a beach, for example, then I'll see a crest, a crest, crest, and a crest. These green lines are the wave fronts, and the distance that separates each wavefront is a wave length. However, the red line shows the direction of wave motion. That's the ray. That's perpendicular to the wavefront. So the wavefront and the ray are always at 90 degrees. However, if we were to have a point source of waves, i.e. if we were to drop a pebble in a pond, it would create radial wavefronts, so they'd move out in concentric circles from the source. Try and draw them properly, which is quite hard, drawing by hand. There we are, but the wave is radiating out from the center of the source, so the rays look like this. Still 90 degrees to the wavefronts, and there's still one wavelength between consecutive wave fronts. So that was wavefronts and rays. So carrying on with 4.3, we're going to talk about amplitude and intensity. Well, amplitude we've heard of before. That's the maximum displacement of the medium, whereas intensity is a new concept and it's defined as the power per unit area. So we've talked about that waves transfer energy, and power is energy per unit time. Well, intensity is power per unit area, and the units are watts per square meter. There's two rules you need to know about, and one is that the intensity is proportional to the square of the amplitude, because energy and therefore power is proportional to amplitude. This means that if the amplitude doubles, so for example I have two waves adding up, meeting and adding up, the intensity will quadruple. The second rule, so let's see, first rule, which you're given in the data booklet. The second rule is that the intensity is proportional to the inverse square of the distance, or I is proportional to x to the power -2, which is the same as I is proportional to 1 upon x squared. That's because since the wave is spread out in all three dimensions, the energy is spread out over a sphere of surface area 4 pi r squared. So if I was to compare the intensity at point A, on the edge of this sphere here, the surface area would be 4 pi x squared, whereas if I was at a point B on the second sphere, which is double the distance from the point source, the energy would be spread out over a sphere of 4 pi times brackets 2x squared, which is 4 times as large as surface area A. Therefore the intensity would decrease by a factor 4, since intensity is inversely proportional to area. Therefore intensity is inversely proportional to the square of the distance from the source. This is called the inverse square law and pops up a few more times in physics. Okay, carrying on with 4.3 wave characteristics. We're going to talk now about the phenomenon of superposition, and it's basically the algebraic sum of displacements of two or more waves travelling in the same medium, meeting at the same place in space. So we're going to have three different scenarios here. We're going to have two waves, a red and a blue. In the first scenario, they are meeting in phase. So a crest meets a crest and a trough meets a trough, or position of maximum displacement meets a position of maximum displacement, and a position of minimum displacement meets another position of minimum displacement. Now, you don't see the individual displacements. What you see is the superposed position, which is the sum of the two displacements. So I would take, let's do it in green, I take this, the red's displacement, and I'd add it to the blue displacement, which would give me a new displacement, or a superposed displacement up here. Here they both have a displacement of 0, so the superposed displacement will be 0. Here the superposed displacement will be 0, and again here the superposed displacement will be 0. But here the two negatives add up to make a larger negative displacement, and you end up with having a position that looks like this. This is actually what we call, we're going to come onto that slightly later, this is what we call constructive interference. However, in our second scenario, let's have the situation where we have the red wave, which looks like this, meets up with the blue wave, which is exactly out of phase. In this case, all the positions would exactly cancel out to give a superposed wave which has 0 displacement. This is called destructive interference. Notice the conditions for constructive and destructive interference is that both the waves have the same wavelength. However, let's look at another final case of superposition where we have a red wave which has a wavelength, or that would be half the wavelength, and a blue wave which has the same maximum amplitude, but it has a slightly shorter wavelength. So what would happen here? Well, we'd have 0 displacements at the beginning and end. Here, since the blue has 0 displacement, the superposed wave is only going to have the displacement of the red, whereas here the two displacements are going to add up to make a larger displacement. Here there's going to be a larger displacement, but here the two displacements are going to cancel out. So the superposed wave will look something like this, and you get the superposed wave again by adding up the individual displacements of the individual waves to result in a combined superposed wave. So also in this subtopic is the concept of polarization, and you can understand it in that waves are a displacement of a medium, and the medium can oscillate along a certain plane, i.e. the x-plane or the y-plane. So if a medium oscillates only in one plane, then we say it's polarized. The opposite of that would be if we have a combination of different planes of oscillation, then it would be unpolarized. However, longitudinal waves cannot be polarized, so sound waves cannot be polarized, and you also have to know that light from the sun is also unpolarized. Now we can polarize light in a number of ways. One is passing it through what's called a polarizer, which can be seen as like a grid, if you like, which only lets light of a certain polarization through. So if we were to pass unpolarized light of intensity I through the polarizer, it would end up being polarized in the plane of polarization of the polarizer, and its intensity would be half the original. However, if we have already polarized light of intensity I0 passing through a polarizer at an angle theta to the incoming plane of polarization, then the outgoing, or the transmitted intensity that we would receive, I, would be equal to I0 times the cosine squared of the angle between the plane of polarization and the plane of the polarizer. This is what we call Marlus's law. And if we were to plot maximum intensity or intensity transmitted against angle, cosine squared graph would look like this. It has a minimum at 90 degrees and a maximum at 0 and 180. And if we were to have two polarizers at 90 degrees to each other, then that's the same as having zero intensity, and that's when we have crossed polarizers. When you have polarizers at 90 degrees to each other, then no light is let through.